Hello. What you're looking at here is an adapter which has been flame cut out of 2-inch thick plate. Um, this is for the auger boring machine. I made a series of videos a couple years ago. I was designing and building an auger boring machine for one of my customers, and it got used in a job using 48-inch diameter casings. There were some teething problems, but they got most of the problems worked out with it. Actually, the part that I designed and built worked fine. There was no issues with that. All the issues came about with the casings themselves and the augers, and sort of the technique on how you push and cut and stuff like that. But we figure we have those problems solved, hopefully. And they've now gotten another job, but this time it's with 42-inch casing, so a little bit smaller. And that requires all new adapters in that to be built. So that's what these are for. Now, it's this one here that's actually the point of the video, this eccentric one. With the auger boring machine, you push steel pipes, essentially called casings, under the road. This is for installing culverts. And then once you get it through, and the augers have cleaned all the mud out, etc., now you have steel casings under the road. You then push concrete pipes, and those are the finished product, concrete pipes. So you push the concrete pipes in, and they push the steel casings out. So when you're done, you have concrete culvert under the road, and the steel casings are all sitting in the ditch on the side of the road, and they can be reused again for the next job. So this adapter is designed like this because the concrete pipe is a little bit smaller than the steel casing that cuts the path for it, and they want the bottoms, known as the invert in sewer and water work, the bottoms of the pipe to be at the same elevation. So we have to build this adapter that the concrete pipe fits in the small diameter, and the concrete pipe has a spigot on the front. So the spigot fits through that diameter, and then it pushes on this adapter, and then the larger outside diameter is concentric to the steel casing, and that's what transfers the load from the concrete pipe to the steel pipe and pushes the steel pipe or casing out of the ground. Now, this was a bit of a rush job. It was supposed to start on the 8th of January. There's since been a delay unrelated to anything I'm doing, which has actually been good. It bought me some extra time, but I had to order all this steel just before Christmas, and the steel supplier has about a 10-day general shutdown over Christmas. And by the time we got the stuff figured out, it was only about 3 days left in the week before the break, and I really had to get this ordered, and I didn't know the diameter of the spigot at the time, so I kind of guessed at it based on the diameter of the other ones, and then I purposely made it a little bit undersized, knowing that I could probably bore it out. And sure enough, actually the steel supplier actually came through and got us the steel before Christmas, so that was good. I was actually surprised, but they were able to do it. And then after Christmas, I got the spigot size, and of course it's too small, so I have to bore it out. The OD of this is small enough that I could turn it on my large lathe. The problem is, it's not the OD that I'm machining, it's the ID. And when you get the ID running concentric on the lathe, the effective diameter, which is twice the distance from the center of the inside diameter to the thickest part of the outside diameter, ends up being larger than my lathe can swing. So the idea I had in mind was that I could probably bore this out on my boring mill. I have these large 3-foot tall angle plates that I could mount this to, and so I was thinking I could mount it to the table and then bore it out, but this is the only boring head I have, And wall hoppers are great. I love it, but it's not going to bore a 35-inch diameter hole. So when I ordered the steel for those adapters, I also ordered this piece of steel, which was just 3-inch thick plate. I got a piece flame cut 3 feet long and a little over 6 inches wide. And my plan was to make a boring, I don't even know what you would call it, a boring slide maybe, that could mount on the milling spindle of the boring mill. And that's what I'm just finishing right now. This detail here allows it to bolt to the milling spindle, which is the more rigid of the two spindles. And then almost like a facing slide, you can clamp down a boring bar holder into the T-slots and you can slide it along to wherever you want. Now this thing doesn't have any adjustment or feed, or ability to face like a proper boring and facing slide would have. But it will allow me to set a boring bar, pretty much to any diameter I want within the range of this machine, and get it roughly to size, and then I can make fine adjustments on the actual cutting tool itself, similar to when you line bore and things like that. Along with that, this is the actual boring bar. This was a bar I actually made when I first got my lathe down there, and I built this bar and a holder to allow me to turn to the largest outside diameter that lathe could swing in its gap. And I built this 18 years ago. I have never used it, so I decided to use it for this. So I cut it down to length, we welded it on, and then faced the back so it's nice and flat, and then drilled the holes with the same, this spacing is the same as the distance between the T-slots on the boring slide. So I'll be able to bolt this on, and then I have this left-hand tool I'm going to try, and this will be sweeping out a circle this way as it goes around. So we'll give it a try and see. My boring mill will go as low as 12.5 RPM, and that gives me, at this diameter, 130 or so surface feet a minute, which should be no problem for carbide. And hopefully I have built everything rigid enough, and the machine itself is rigid enough that it can handle a diameter that big. It'll be a good test for it, because the very first cut is going to have to be cutting through a flame cut surface, which is definitely harder than the parent material. So, but I'll finish up this slide, and then we'll see how it actually works. Nice finish, very smooth. And it measures to within, it's just a little bit less than a thou oversize. 34 1/8 is finish size, and it's 34.1257, I think. Maybe if you can measure that accurately at that size, but well, the boring is over, and I've got the boring slide off the machine now. It's just sitting here. I just wanted to show something, because when I had the boring slide mounted to the machine and I was using it, I actually had studs through here with flange nuts from my clamping kit holding it on, and that wasn't the original design. I designed it, I counterbored it so I could use socketed cap screws. I had ordered the cap screws because it's a certain length, but they hadn't come in yet when I needed to use it, so it wasn't going to affect the function at all, so I just used studs and nuts. But the original design, you can see the socketed cap screws are there. They stick out. Oh, you get about a little over an inch of engagement, which is plenty for a 5/8 thread. And that's them there. The idea was that I would counter bore them so that the heads were slightly below the bottom of the T-slot, and then that would allow the boring bar to be slid anywhere along here without any interference from the socketed cap screws. As luck would have it, they showed up the day after I finished the job, but anyways, it all worked out. So, and then I also got some shorter ones that will eventually be put in here. Same thing, I'll counter bore these, and they will fit down in. That's something I'm going to do later. I got a little problem in that the shank of my counter bore isn't tall enough to clear this, and the chuck will hit here. So when I have some time, I'm really busy right now. When things slow down, I'll make an extension and I'll counter bore those. On rotating stuff like this, I prefer to use socketed cap screws and counter bore them, as it's one less thing that's sticking out that can either hit a piece of work or grab hold of you and pull you in. It just makes it a little bit safer. So, and in this case, it was the only way to hold it on and not interfere with the T-slots. So I'm pretty happy with that. It worked out really well. I ended up going up to 40 RPM. I started out at 12.5. On the finishing passes, I was going 40. Each of the scenes I showed before this, I show the RPM, and it turned out going a little bit faster made things work better. I guess you just kind of have to get a minimum speed for that tool to work properly, and it turned out really well. There's the just about finished product. The only thing I have to do now is I got to drill a hole through the wall for an eye bolt, a long shanked eye bolt with a nut, which is what they requested for lifting. We just welded 4 channels on, and their job is just to sit inside the steel casing and pilot this, and then in use what they'll do is they'll push it in, and then they'll just get it with a couple of tacks, weld it. Once you get the first concrete pipe in and start pushing, none of it matters, because this goes into compression and this part essentially gets squeezed. I had mentioned the diameter there earlier. I measured it with my large inside mic. I had a video about this micrometer a few years ago. It measures up to 30 some feet. It's kind of crazy, but anyways, I'm not sure. I've never really measured big diameters like this, or I never really measure them too often. I don't have anything to check it against, so I don't really know how accurate it actually is, but as accurately as I can use it and as accurate as it is, I was able to hit the size within better than a thou of what I wanted to. And essentially what I mean by that is I took a measurement, I adjusted the tool, and I took a final cut, and then I remeasured it when I was done, and it was within 7/10 of being on size. So, and the way I adjusted the tool, I wish I still had this on the machine so I could show it, but I didn't use a dial indicator. What I did was I would raise the head up. I would have the tool pointing down so that the cutting edge was pointing into the bottom of the bore. Then I would raise the head up by the amount I needed to extend the tool out. That would pull the tool away from the bore. Then I could loosen the tool, drop it down until it touched the bore, and then retighten it. And that's how I would get my tool offset. You know, I suspect it's probably not quite as accurate as a dial indicator, but it was good enough that, you know, between the two measured cuts I took, I got it to on size in less than a thou. So right now I've got this other part in set up on the angle plates. I have to drill a hole through the side as well for the lifting eye, and I'm going to do that using the angle plates since they're already on the machine. One advantage to doing it this way is I'm going to drill the hole through here. I want to be pointing at the center of the circle, so I need to find the center. By having it up on the angle plates and setting it on the steel block, the steel block's there to protect the table, but I can come in now and I can pick up this edge, which puts me on the diameter down here, and then I can just come up half the diameter. And then this being a rotary table, I can just index this 90 degrees and have this surface pointing at the spindle. Then I can come in and I can pick up both sides and split the difference and find the center of thickness, and then I can just drill through. And I'll do the same for the other one. Had I been on the ball and paid attention, I could have set that one up slightly differently and then just drilled the hole after I finished boring it. But I was kind of wrapped up with the whole first time using the boring head, trying not to get in its way and get hit by it, stuff like that. So I wasn't thinking that quite far ahead on the actual machining process. So with practice, a guy will be able to think ahead like that. So anyways, that's about the end. Maybe I'll show a bit of footage drilling holes, but that's fairly straightforward stuff. Thanks for watching.